Welcome back, class. I'm Dr. April Ström, and I'd love to be able to set up this thinking task for you. So imagine that the graph here shows the velocity in miles per hour of two different cars, and we're tracking relative to time measured in hours. And that we have an interesting point right here at exactly 1 hour. And so the question is, who went the furthest in this particular graph? Just knowing this information, you have no idea what the function equations are, anything else. Who went the greatest distance? Now you notice I'm asking this question because we have velocity over here in the vertical axis relative to time. So now I'd like you to just to pause for a second and think to yourself, which of these cars, car A or car B, went the furthest? So now that you have thought about that graph, I would like to kind of showcase something interesting for you. So I've separated the two graphs. So on the left here, we have the graph of car A, and on the right, we have the graph of car B. Now, if you're thinking about distance, but you only know velocity and time, can you imagine a way that all three of those quantities actually are connected? Well, hopefully you remember this little fact about those three quantities, that in fact, when we take our velocity, or our speed, you can think, and we multiply it by time, well, that gives us distance. And that was the question I posed of which of these two cars actually went the furthest. So this is really all you can leverage, hopefully leverage in your mind, that if I take the quantities of velocity and multiply it by my time that have elapsed, I better get distance. Well, it turns out when we multiply a couple of quantities together, it actually is an area. You may not have ever thought about that, even back when you were first learning multiplication of, say, 3 times 5 when you were in elementary school. Well, it turns out 3 times 5, the product of those two values, reveals an area to us. Nowadays, they actually really focus on area relative to multiplication, but a while back, that wasn't necessarily the case. But it is something we need to think about here. So if we connect area and velocity and time and the distance all together, it turns out that when I need to know how far car A went, say in this first 1 hour time, and I multiply these quantities together to give me distance, what I'm really graphically talking about is, in fact, the area under the curve for car A up until I hit the time axis. So I'm going to shade this region in because I want you to, in your mind, be thinking about the distance, whatever it might be for car A, is revealed to us by this shaded region that I have here, some quantity. Now, consequently, when I think about car B, however, I still need to be thinking about area in terms of velocity and time being multiplied together. And so, of course, when I multiply those quantities together, it turns out, once again, that the distance, velocity times time, the distance that car B traveled can be shown using the area under the car B curve. So this little area right here would give us the actual distance that car B traveled, if we could calculate it at this point. But you can even see something interesting if you just think about multiplication as an area itself. We already visually see that car A must have traveled further, given that the area here under car A's curve is larger than the area over here under car B's curve. Now the question becomes, how much further did car A travel than car B? So I want you to pause for a moment and think about that question. How much further did car A travel than car B? And as you're thinking about that, think about how we could use the shaded regions depicted in these two graphs to help us figure out how much further car A went than car B. So now we're back to the original graph where I have both the graphs of car A and B shown on the same grid. So back to the question of how can we find out how much further car A went than car B? And of course, leveraging these areas under the curve. If you could imagine the area under the A car A curve here as being depicted by this pretend shaded region. And again, car B underneath that curve, the blue curve. If I need to figure out how much further car A went, well, it would be the section of these areas that do not overlap. The area underneath the car B curve already overlaps with car A's area, aka distance that car A traveled. And thus, if I want to know how much further car A went, well, I need to figure out somehow, some way, what the area is over for this particular shaded region in purple. This is not a region that overlaps between those two curves. But what I'm essentially gonna need to do is think about the area for car A, and then I need to subtract off the area for car B, and that will reveal for me this purple shaded region. So in my next video, what we will do is take a look at this problem again, but with functions attached, and we will go through the integration that's needed to be able to calculate for certain what this shaded region actually is. So stay tuned for my next video and be sure to like and subscribe to our channel.